Okay, today is lab 4, friction loss in the steady pipe flow. And today we don't have any lab part of the video because the procedure is almost the same. And the only difference is we're using the two pipes from the bottom. If you check the video last time, you will see the two pipes, cast iron pipes on the bottom. It's just a simple pipe with no contraction, expansion, restriction in the middle of the pipe. So, and the only difference is unlike the Venturi, the Venturi is something like this, right? We have contraction if the flow is coming from this side. So the manometer vinyl tube is located before and after the contraction. Okay, so it's like that. But and the whole pipe is extended. Okay, our focus is only this local area, but in this lab we have two types of the cast iron pipe. The first one is 2-inch, and the second one is a 4-inch diameter pipe. Okay, so the manometer tube are connected over a length of L. Okay, so the reason we do that is we want to check the pressure drop along the whole length of the pipe. Okay, and the L is 182-inch. Okay, so there will be two tubes connected to the manometer U tube. Okay, something like that. The difference is we have a smaller pipe, which is a 2-inch diameter, and then we have a larger pipe, which is a 4-inch diameter. And the L is the same. Okay, the L is the same. It's both 182-inch. So the spacing between the tubes are 182-inch. Okay. Let's see. Okay. So let's talk a little bit about the theory. And well, it's almost the same, right? The energy equation, P1 plus alpha B1 squared over 2T plus Z. And since it's a horizontal, right? Since it's a horizontal pipe, so the Z should be equal, right? And because the cross section of the pipe doesn't change, right? So the A1 in here equal to A2 in here, right? So which means V1 A1 should equal to A2 V2 A2. Okay, if A1 equal to A2, so the V1 should equal to V2 too. Okay, so this part can be canceled out. Z can be canceled out. Okay, so the whole equation will only keep the P, the pressure part, and the head loss part. Okay, this head loss is the head loss, the water flow. So this equation is established between the two cross section with the tube attached. Okay, So the head loss is the head loss between these two cross sections. Okay. Let's move on. Okay. Here's the, so our case is not like this. Okay, it's not like this figure. Okay, this is just a illustration. In in this lab, the A1 equal to A2, so there's no shrink like this, and the pipe is horizontal, so Z1 equal to Z2, A1 equal to A2, B1 equal to B2. Okay, so the whole energy equation will then become head loss equals to P1 minus P2 over gamma. Gamma is the specific weight of the water. Okay. And as you remember, well, last time we introduced the manometer equation for the pressure. Okay, how we calculate the pressure. Okay, we have a delta H. The delta H, the delta H is the elevation, the surface of the manometer fluid. Okay, in the YouTube, right? Then you can see if the right side is higher, the left side is higher. It doesn't matter. You just need to find the difference in the height, and that's your delta H. Once you read that the height difference from the manometer, just record it times gamma m. Gamma m is the specific weight of the manometer fluid. Okay, minus gamma. Gamma is the specific weight of the water, and over gamma. Okay, that's the equation of the head loss. Okay, so this part, okay, let me get the pen. So this part, delta H, gamma m minus gamma, is your P1 minus P2, your delta P. Okay, it should be exactly the same like we already had in the lab 3. Okay, so delta P over gamma. So it's this part over gamma is your head loss. Okay. Yeah, I think it's pretty straightforward. Then, because we have the gamma m minus gamma over gamma. Okay, so this equation can be simplified to equation 4.4. Okay, so basically gamma m over gamma minus gamma over gamma, so it will become Sg minus 1. Okay, so the Sg is the ratio between the two specific weight. Okay, and as we know, the specific gravity is 1.95. Okay, and minus 1. So the equation will be pretty simple. The head loss equals to 0.95 times delta H. Okay, and the unit of the delta H in this lab should be millimeter. Okay, just like last lab, should be the same. Unit is millimeter. Okay, so once you get this, I think that's pretty much a very important part of this lab. We need to calculate the head loss over the lens. The lens is 182 inches. So once we get the head loss, we're able to use the Darcy-Weisbach equation to find out the Reynolds number or the friction factor, okay, of the cast iron pipe. Okay, and since we already get the head loss, right? The head loss using the pressure difference to calculate the head loss. And what is this part? L over D. The L is the difference between the two cross section. okay, the distance between the two cross section, which is 182 inch. Okay, so you need to do the unit conversion. Okay, you have to change it to millimeter or meter. It depends on your calculation. You can convert everything into the English unit, or you can convert everything into the British, the SI unit. It depends. Up to you. Okay. Okay. So L is 182 inch, and the D, what is D? D is the diameter of the pipe. Okay. So for case 1, probably 2 inch, and for case 2 is 4 inch. Okay, that's the D. And V squared over 2G. Okay, G is the gravitational constant, and the V, just like last time, how you guys are still remember how we calculate the uh, the discharge of the pipe, the flow rate of the pipe, correct? We have our weighing tank, okay? We use the stopwatch to count 40 seconds, 50 seconds, 1 minute. So we weigh the water in the tank, and we divide, we convert the weight of the water into the volume of the water and divide it by time. So that's the flow rate in the pipe. Okay, from the flow rate, okay, once we got the flow rate Q using the data, okay, just divided by the area, the cross-section area of the pipe, it will give you the V. Okay, so the 2 inch will be pi d squared over 4, correct? So you just plug 2 inch into this one, you will get your V. Okay, that's pretty straightforward. So we know the HL, okay, by using the manometer, the data from the manometer. We can calculate the V by using the data of the weighing tank. Okay, so we have everything in here except for this F. Okay, so the F will become your HL times D times 2G over LV squared. Okay, so that's how we calculate this friction factor F in here. And also F is a function of the Reynolds number and E over D. Okay, and we need to look into this one. We also want to calculate the Reynolds number for each pipe. Okay, in different flow rate, because we are able to open the valve of the pipe. We adjust the opening, so the flow rate is different. Okay, we want to start from the very small flow rate and trying to make the laminar flow in the pipe, and then we gradually open the valve a little bit by a little bit, so the flow rate is bigger and bigger. So the Reynolds number should be bigger and bigger, right? Because when the flow rate is bigger, we're able to create a probably when the flow rate is very small, it's laminar flow, and if it's become larger, it will become the turbulence flow. So the Reynolds number should be escalate pretty fast. Okay, so in the data set I give you guys, it could be I don't know, it could be 5 data or 10 data points for each pipe. So you will see after the calculation, you will see which part is in the laminar flow. As you see in here, it is that in most circumstances, the flow of water in the pipes, if the Reynolds number larger than 2000 is turbulence. Okay, if the Reynolds number is less than 2000, it's a laminar flow. Okay, you're able to judge if it's a laminar flow or turbulence flow just by calculating the Reynolds number. The Reynolds number equals to V times D, the diameter, over this one, over this little V. Okay, the V is the kinematic viscosity of the fluid. Okay, you're able to find it out. Okay, you just open your fluid mechanics book and find out kinematic viscosity of the water. Okay, and since it's room temperature, you can just use like a probably 70 or 75 Fahrenheit. Okay, use that number. Okay, because the kinematic viscosity is depend on the temperature. Okay, you can just use yeah, let's say just use the 70 Okay, use that number. Okay, that's one part I need to check in your lab report. Okay, if you find the right number. Okay. Okay. Okay, that's pretty much it. And let's go over a little bit about the procedure. Okay, turn on the main pump. Okay, main pump to establish a constant head in the head tank. That's basically the first step I did in the video last time. Is I opened the pump so until the head tank is full, so all the pipes will have the constant head. Okay, make sure the manometer board is functioning properly. In this step, you're basically checking the manometer fluid level. Okay, on the right side and the left side should be equal. Okay, so because at the beginning there's no flow in the pipe, the pressure at the two per section should equal. Okay, so select the 2-inch pipe first to measure the pressure drop across. Okay, open the appropriate valves for the selected pipe. Okay, so we choose the 2-inch pipe to start. We open a little bit, start at the very low flow rate. Okay, which means you just open a little at the beginning and let the flow stabilize, then read the head from the tube manometer. Okay, so which means when you open the valve, the reading on the manometer, should vary. It's changing. You have to wait until the reading on the manometer is stabilized. So once it's stabilized, read the delta H, okay, and use the weighing tank record the discharge. Yeah. So from this step, you're able to get your delta H, which means you're able to calculate your delta P and the head loss already. And in this part, the weighing tank has two readings. One is WI, which means the weight, initial weight. And another one is W final. Okay, so the W final minus WI is the weight of the water, during the specific time period. Now let's see 20 seconds. Okay, so WF minus WI over gamma water. Okay, that's your volume of the water. Okay, and over T, like this. That's for example 20 seconds. That's your flow rate. Okay, from the flow rate, get your V. Okay. Then plug the head loss and the velocity into the Darcy-Weisbach equation. Okay. So the analysis of data is pretty simple this time. Okay, using the experimental data, calculate the head loss. I already told you how to do it. And the friction factor F, right? You have the head loss, you have everything on the right-hand side of the equation, but the F. So you just move it, the rest of the equation, L over dv squared over 2g into the left side. You're able to calculate this F, okay? So I want a table. I want a table with all the result of the head loss and the friction factor, okay? So one table for one case, 2-inch pipe, one table, 4-inch pipe, another table, okay? Plot the head loss versus Q for each of the two pipe diameters, okay? So that's two plot, okay? So the first part, two tables, and this one, two figures, okay? Head loss versus Q, so it's a scatter plot. Basically means, I mean, if from the equation you will know the head loss is positively proportional to the velocity. So if the discharge, the flow rate is bigger, the head loss is bigger. So it should be something like that. I don't know the trend. It could be linear proportional or cubic or second order proportional. So you just draw the scatter plot. This is your head loss, and this is your Q, and write the trend line, okay? And plot F and RE in the two pipes. Okay, that's another two figures. The y-axis is your friction factor F, and this is your Reynolds number. Okay. What is the Reynolds number? Just remind you, Reynolds number is equal to V times D over kinematic viscosity. Okay, so if the Reynolds number is bigger, the friction factor is bigger too. Okay, so it's another scatter plot. Okay, and use the Excel to get you a trend line like this. So two figures, another two figures. So it's pretty straightforward. We need four figures for analysis data and two tables include the head loss and the friction factor. That's pretty much it for the analysis of data. Okay, and just use your own words to answer the question in the discussion point. Okay, that part is very important. I hope you guys could finish. Okay, and regarding the data table, it gives you all the detailed information you need. Like for the first table, it's a 2-inch pipe. The L is 182. The second table is for the 4-inch pipe. L is 182 inches. Okay, and this is a weight, initial weight, final weight, and the times. Okay, the manometer, but here the unit is feet. But when I gave you the data, it could be in the other unit, because in the lab the unit in the manometer is millimeter. Okay, so I could probably give you the H1 and H2, which is the surface elevation on the right side and the left side of the manometer U2. So the unit could be in millimeter, and I think that's pretty much it for today. And please let me know if you guys have any questions regarding this lab. every Monday and Wednesday. I hope you guys could start earlier rather than ask me question 3 days before the the, the deadline. Okay. Okay. Thank you so much. That's it for today.